In this video, I want to bring together some of that which we've talked about in the last few videos and talk about the example of making inferences about the population mean test score, given that we have assumed a normal prior density and a normal likelihood. So the prior here for our parameter theta is that it is normally distributed with some sort of population sort of mean, which I'm going to call here theta 0, and some variance, which is just given by sigma squared theta. So you can sort of think about theta perhaps here as representing the sort of mean test score in from one individual year, and theta 0 here perhaps represents the sort of over many years the mean test score. And what we're assuming here is that we've also got a normal likelihood, so an individual's test score in a class, call it xi, is itself normally distributed about this sort of population year parameter theta and some variance, which I'm going to call here sigma squared x. And we know that in this case and in all cases, the posterior density, the probability of theta, given that we've observed a vector of observations x, is just equal to, well, we could use our Bayesian formula, but I'm actually not going to use equals, I'm going to use proportional to the product of the prior density, the probability of theta, times the likelihood, which is the probability of our vector observations given choice of theta. And we know that we can write that this is proportional to this because of the fact that the denominator of Bayes' rule, the marginal probability of the data, is itself theta independent. So all theta dependence is contained within these two terms here. And we know that in this case of when we've got our sort of normal prior and we've got our normal likelihood, we've already worked out what the specific form of the posterior density is. It's normal with a mean of theta primed and a variance of sigma squared theta prime. And theta primed and sigma squared theta primed are themselves sort of weighted sums of parameters within the prior and the likelihood functions. But what I want to talk about here is kind of the intuition as to what's going on, because what we're taking here is we're taking our prior and we're multiplying it by our likelihood, and that basically determines our posterior density. So what we can think about here is we imagine that we've got our sort of prior density here. So we've got theta as our x-axis, and our prior density, if we imagine that all of these sort of previous classes had a sort of overall mean theta 0, which was equal to 70, and they had a sort of overall variance which was perhaps equal to 10 in terms of the sort of variance of the means of those classes. So perhaps our prior density looks something like this. So it's got a mean of 70 in this case. And then if we think about what would, in this case, our likelihood look like, if we imagine our sort of new class has a mean of, let's call it x bar, which is equal to 60, and the variance of a sort of class about their mean is fixed from year to year, and it's got a value of 25. And we can imagine that this would itself, the likelihood function, even though it wouldn't be on the same sort of y scale as the prior. So this, just to be clear, this mauve case here is the prior density, and this, which I'm about to draw in orange, is a likelihood. The prior is itself a proper probability density, whereas the likelihood is not, so it doesn't integrate to 1. So here we've got having a mean of 60 and a variance of 25. So it's actually slightly wider than our prior density, which I'm sort of trying to illustrate here, even though it looks a bit asymmetrical here, but you get the point. So we know that the posterior is the product of the prior and the likelihood, and hence what it's going to be is it's going to be a sort of mixture of these two distributions here. And by mixture, we're going to end up with a posterior which is some way between these two extremes. And it's hence going to have the form which is going to look something like this sort of yellow line here. Although it depends exactly as to the sort of value of theta 1 and its sort of theta primed and its width, depends somewhat on the amount of observations we have. Because if we have lots of observations, then it's going to be weighted much more towards the sort of maximum likelihood estimates, which in this case would just be 60, so it's going to be weighted more towards our likelihood and further away from our prior. But I don't want you to take my word for this. So what I've actually done is I've coded this up into MATLAB so that you can actually go ahead and do these simulations yourself. So what I've done here is I'm starting off with a sort of prior density which is normal with a variance of 10 and a mean of 70, just as I've said here. As I should say, this is actually different to what I sort of stated in the original example introduction video. I've just changed these values just to make them a bit more sensible, but it doesn't matter too much. And we're assuming that we're starting off here with one data point in our sample that's got a value of 60, and when we generalize to sort of having 2 or more data points, this is going to be its mean, and it's got a variance of 25, even though you sort of imagine that one data point itself doesn't actually have a variance, but we can sort of ignore that for the time being for when we generalize to having more than one data point. So if we go ahead and run this, what we see is that we've got a prior density which is centered on our sort of value of 70, our prior population mean test score, and then we've got a likelihood which is centered on the maximum likelihood estimate of the sort of population mean test score, which is 60. And if we go down here to the bottom, we note that the posterior is some way between these two extremes. And another thing to note is that the prior and the posterior are themselves proper probability densities. And by that I mean that they satisfy the conditions for a probability, meaning that they have to integrate to 1. Whereas notice here that the likelihood is itself on a completely different scale. It's sort of 8 times 10 to the power minus 32 as the top of the likelihood scale here. So the likelihood here is very, very small. And hence the likelihood is itself not a probability density when you consider it as a function of theta. So now what we can do is we can think about, okay, let's imagine that we increased the amount of data which we have. So we increased the number of observations, the number of individuals in our class to 2, and then what we should imagine is going to happen is that our posterior density as to our posterior inferences about the population mean test score should weight slightly more towards the likelihood because we've got that much more data. So if we do that, the prior and the likelihood are unchanged in terms of their positioning, although the likelihood here has changed in terms of its scale. And notice that the posterior is now edging further towards the likelihood. So the sort of mean of the posterior is itself getting closer to the likelihood, and that's what we should expect because we've got more data. If we continue increasing the amount of data which we have, so let's say we increase it up to 5, then we're going to see here that the posterior is even closer towards the likelihood, and the prior is essentially be giving less and less weight here. Just finally, just to say that the likelihood here, the scale on it isn't exactly correct by virtue of the fact that I've essentially scaled or kept it sort of normalized to some extent such that I can actually plot this, because you notice that it's actually varying over a number of different orders of magnitude here. But the sort of general shape of the likelihood and sort of any sort of inferences or any intuition which we derive therefrom is pretty accurate.